Hello, thank you for joining. Today I want to talk with you about entity resolution, more specifically about entity resolution in real-time manner and at scale. I'm Stefan Berkner, and I'm the Chief Development Officer at TLORES. TLORES is a serverless entity resolution tool for various use cases, but with a strong focus on fraud, KYC, and AML. I consider myself as a passionate software developer and have been working in entity resolution space for probably at least the last 10 years. So let's start with defining what entity resolution is. So entity resolution helps determining whether two or more records in dataset refer to the same real-world entity. It helps to improve data quality by identifying and eliminating duplicate or redundant records, and it enables data integration by linking records from different sources. And I could probably now continue, and it's probably going to bore you, as I don't know, doesn't seem to be super interesting. So let's actually switch the topic. This is Tilo, my son, and also the name provider of our company. And he too is an entity resolution expert. It's just that he's not so much active in the fraud space, but rather in the Lego and puzzle sorting space. And as much as he likes to puzzle, he also likes to puzzle with multiple sets at the same time, honestly creating huge chaos. The challenge is that after he's done, he puts everything back on a single stack. So when I ask him to clean up, he has to do all the work again of identifying which piece belongs into which box. And this is actually similar to what entity resolution does. The thing about him is that for him, it's really easy to distinguish what belongs into which box. He quickly recognizes if, for example, two puzzle pieces are similar, and for this he uses different attributes like color, size, or shape to make his decision. The issue is, of course, he's only able to handle this fairly small amount of entities and records. So entities, that means in this case, puzzle sets, and records are the puzzle pieces. Unsurprisingly, he's also fairly slow at it. And as he's just 5 years old, he of course also sometimes makes mistakes. And last but not least, he's kind of difficult to scale. So there could maybe be a second Tilo or a third Tilo, but I guess that's enough. So what's special about this is, in general, in entity resolution, it's easy for us to compare two different pieces. Well, what we have in our business world is typically that that you have different kind of similarities, like text similarity, for example, with the easiest being text equality, so the exact same text. But we also can have, let's say, more complex things like fuzzy matching, such as Levenshtein distance, metaphone phonetics, cosine similarity, or Jacquard distance. In other cases, for example, when it comes to geographical or temporal similarity, it's also trivial to calculate the actual distance between two objects, or for example, the time between two timestamps. For images, audio, video, you can use something like locality sensitive hashing techniques, such as p-hash or random projection. I won't go too much into the details of that, simply because it's fairly simple compared to single records and decide whether it's similar or not. The challenge is rather when it comes to comparing millions or even billions of records with each other. The reason for this is that when we need to compare every single record with every other record in our set, it's creating a quadratic complexity. For example, in a set of only 20 records, I need to make exactly 190 comparisons to have everything compared with everything. For still a fairly small set of only 100,000 records, that number has already grown to almost 5 billion comparisons needed. Presuming that each comparison takes, let's say, 1 millisecond, and there's no parallelization in place, that would take almost 58 days just to compare 100,000 records. And we're not even close to the range of millions or even billions of records. Fortunately, we can divide this problem into smaller problems by putting each of the records into a so-called bucket, and then only comparing the items of each bucket with each other. For Tilo's puzzle piece, we could, for example, use the dominating color as a bucket key, or in a more advanced version, we could even assign one piece to multiple buckets if you're only considering multiple colors of the piece. Splitting the records into multiple buckets helps reducing the number of comparisons and leaving us basically with the overall performance being based on the largest or the size of the largest bucket. It's also simple to implement. Just take one or more attributes as a bucket key and then parallelize the computation for each bucket. However, typically this is implemented as a batch process. Once the process is done, your data is already outdated. And eventually you need to construct the actual entities using a connected component algorithm. That means you need to identify that A matches with B, B matches with C, and C matches with D, and so on, and then assign this resulting cluster with an ID. One might now be tempted to use some kind of a real-time recursive search. Don't do this. It might work well for not very deeply nested data, but as soon as you have actually deeper nested connections between those records, it will become slower and slower to retrieve the data. It might even be that it is so slow that you need to stop following the untraversed edges. For example, in a fraud use case, you could imagine that in that case, when cutting off parts of the entity and not seeing the holistic picture of the entity, it would be possible to not detect all cases of fraud. So really, don't follow this approach of recursive searches. So how can we get closer to a real-time solution? Well, let's split the buckets into even smaller buckets. Ideally, each bucket or index key contains only the data that has a very high likeliness of belonging together. I'm going to show you an example of such an index key in a second. But for the moment, let's imagine this index could be stored in a traditional SQL database or in a key value store such as DynamoDB. As a general rule, each index key should only contain a few hundred records, ideally. And also each record should be stored in multiple small indexes. So rather than creating many different indexes, many large indexes, you should rather create many different small indexes. Whenever a new record arrives in the system, you set use that index key to find possible matches, filter them accordingly for actual matches, and then assign the new record to an existing entity. If one record matches with multiple entities, simply merge them. If entities or those entities could, for example, be stored on a file system, or as we do it, store them in an object storage such as AWS S3. The nice thing about this is, in a real-world application, the individual records will usually vary a lot. That means the likeliness of two incoming records affecting the same entity is quite small. Hence, it's possible to parallelize the processing of every incoming record. And again, in TLOS, we're therefore using serverless functions, so more specifically AWS Lambda for this, where we basically process in each Lambda request a single record and assign it to its entity. Any other approach they can do some kind of parallelization, of course, also works. Another aspect that's often forgotten is to store the links between two matching records. And this enables real-time data deletion, traceability of the results, and also provides valuable insights about each entity. If you, for example, can see how the records belong to towards each other, it's easy for you to understand the value behind it. So for TLOS puzzle piece, a possible index key could be based on the color, size, and shape of the piece. However, there are still two issues with that approach. Same data, for example, creates the same index keys, eventually leading to quadratic growth issues again. Let's, for example, consider a valid customer who's always ordering in the same shop with the same name, with the same address, over and over again. That will always end up in the exact same index. The other issue is non-indexable fuzzy matching that requires two records. For example, the classical example there is the calculation of a Levenstein distance, or in the puzzle use case, to only match if the size of two records is roughly within a 20% margin. I won't go into too much details of this challenge, but it's obviously solvable via some kind of clever index creation there. I also mentioned before that ideally we should also store the links or edges between two matching records. And this would allow us to split entities when a record is removed at a later point. So that means you could, if a single record is the only connecting piece between two parts of the entity, and you remove this record, then of course all the connections between part A and part B are run, and then you would be able to split this entity again afterwards. However, again, the issue with the edges is that, again, same data creates a lot of different edges. As you can see here, everything looks good if you have only 3 edges, 3 nodes. With 6 edges, it's already, again, at quadratic growth. So to bypass the issue of with the same data in both indexes and edges, we can introduce something we internally call deduplication, which means we could identify whether or not 2 records are identical in the matching relevant attributes. However, it's not required that they're identical in all attributes. For example, in the orders in an e-commerce shop, you will have differences in what was ordered, when was it ordered, and probably a lot of other attributes. But matching relevant data for that use case, typically the name and the address, is still the same or very similar most of the times. The advantage in that case is that we don't need to index those non-identical duplicates, as they would create the exact same key, the exact same index key as the original. We also don't need to store the edges in that case, as it also would be exactly the same as the original. The only thing we need to remember is to replace the original with any of its duplicates in case of deletion. I would like to give you a very short demonstration. Obviously, I can't show the performance of this, but at least I'd like to show you a little bit how it looks in our system. So let me just ingest a single data set here and search for it. And as you can see right now, we have only one person here. That's, by the way, artificial data. Let's add another one, and we again can search for it. And this is basically how a duplicate looks like for us. We could here, for example, look at the records. So we see Mariana and Mariana in both records. It's the same. Probably most of the other attributes are also the same. Let's add something more. And as you can see, the entity gets more and more complex as we are constructing it. And let me add a little bit of other data here, and then that should be fine. So by now you should have an idea how this works. So whenever we're adding new data to an entity, we can simply add it to the existing entities, possibly merging multiple entities, and yeah, therefore having a full picture of our customer, a company, or whatever you consider an entity in your use cases. So that already brings me to the end of my talk. I hope I was able to provide you with a basic idea of what entity resolution is about, and that I was able to explain at least one of its challenges. It's obviously much more complex than just that. Yeah, if you have further questions, feel free to ask them now, or of course contact us at any time. Thank you.